Hey there, folks. Had a question about section exercise 3.7.9 and section 3.7. This is a free damped oscillator. In other words, we've got a mass, a spring with a spring constant, and we've got a damper with a damping constant, but we have no external forces driving the system. I'm not going to talk about explicitly how to solve this, but it's a good opportunity to remind folks about how to approach an exercise like this. You'll recall that you're trying to construct a differential equation of the form m u double prime plus gamma u prime plus k u equals 0. And in particular, you're trying to identify the mass, the damping constant, and the spring constant. So the way that you read these exercises is as little clues for determining these three constants. This underlined bit in red is going to help you determine the spring constant k. You know mass times gravity, and you know the length that the spring has been stretched by this particular mass, and that'll let you solve for k. The damping constant is given explicitly like this, and we see the presence of this unit that you may or may not be familiar with, the dyne. A dyne is a gram centimeter per second squared, and then the units on this damping constant involve an additional second per centimeter. And if you work all that out, the centimeters cancel, one set of seconds cancels, and you end up with grams per second, I guess. Yeah. But I just want to sort of emphasize that these are the units on a dyne. And to talk a little bit more about units, most everything is given either in grams or centimeters, and the time period is seconds here. You can see the seconds units lurking here. So you should use grams, centimeters, and seconds units as you build this. So keep the mass in terms of grams, keep gamma in terms of this 400 thing, and whatever you figure out to be k, make sure that that's also in units of grams and centimeters. Okay, and then you build once you figure out m and gamma and k, you build that differential equation, and this sentence here, if the mass is pulled down an additional 2 centimeters and released, this will tell you what the initial conditions are. You can plot, you can solve it at that point, and then plot u versus t using whatever your favorite piece of graphing software is. When you do that, you should get a damped oscillation, something that looks like this. Look in the book for the definition of quasi-frequency and quasi-period and use those definitions. They're listed in section 3.7. And then the ratio of the quasi-period to the period of the corresponding undamped motion. That would be looking at, that's also in the book, but if you wanted to solve it again, you could just zero out the damping constant and then solve it again with mu double prime plus ku equals 0. And then last, find the time tau such that the amplitude u is less than 0.05 centimeters for all t bigger than tau. So you have this damped oscillation. It's slowly kind of fading away to 0. I've sketched in, just by way of example, 0.05 and minus 0.05 based on this quantity here. And you're really just looking at this damped oscillation and trying to figure out when it gets into that range and stays in that range forever after. I mean, clearly it enters that range here, but then it leaves the range here, and then it goes back into the range here, and then it stays in afterwards. So you want to find this point tau where the oscillation enters the plus or minus 0.05 range and stays there forever after. This you can do by looking at the plot and just estimating the correct tau value. You don't need to find it out to 16 decimal places. Just give an estimate. I hope this helps.